Hey, good morning, students. And today we'll be learning another classic algorithm in machine learning, and that is a support vector machine. Um, yeah, if we turn back 10 years ago, one of the most popular algorithm would be support vector machine. So the idea is extremely simple. Given two sample of classes, uh, support vector machine asks a very good question, that is, which line would give you the best line, A, B, or C, right? And according to the support vector machine, the best line is B because it possesses the widest width between the support vector, which is this one and this one, which support the vector, or you can say the closest samples to this boundary, right? And for this support vector, it can be more than one. But obviously for B here, we can see that there's a one yellow here and one purple here to support this vector, but it doesn't necessarily need to have only two. It can be multiple from different classes, and it doesn't have to be equal, right? But anyway, that comes to name support vector machine. So let's take a look at the problem definition. So the hypothesis function is simply a line, right? And in which you take the sign, and then that should give you the classes, which is -1 or 1, right? So in support vector machine is a binary classification problem that classifies things into -1 and 1. Because of that, we can also write a constraint that if it's less than equal to -1, then it belongs to class -1. Otherwise, it's 1, right? And if we want wrap this up into one equation, we get yi multiplies the wtx plus b is greater than equal to 1, right? And you can check that is correct, right? Because yi, if it's 1, it's the same equation as this. If it's -1, we just simply flip the sign. Now, so how do we turn this into an optimization problem? Well, first of all, we have to derive what is the width of this margin. And if you want to take a look, you can read this file, which is not inside the code along, but inside the SVM with the same name. I have derived and show you that this width is nothing but 2 over the magnitude of W, right? You can see. And but we can also turn this into a minimization problem, right? Because if it's 2 over magnitude of W, we can just turn it into a minimization problem that is 1/2 magnitude of W square. You may wonder, why do we have square here and 1/2 here? And this is just for mathematical convenience, right? Because as we know, the optimization problem doesn't change. The optimal numbers doesn't change even though we change the constants. At the same time, we can put it that such that is constrained within this, right? Which is based on this constraint that we have defined. So if we have defined our problem so clearly like this, we can then use something called Lagrange, right? So that is the whole purpose of framing our problem in this format, because Lagrange exactly want the problem to put it in this format. One very good question is why we can't use gradient descent right away. And the answer is because there's constraint, and given constraint, you cannot simply use gradient descent. And here we can use Lagrange. So according to Lagrange, the idea is very simple. You have to write the equation according to what they specify. So first you have to specify what you want to minimize, and then what is the constraint. And the purpose of Lagrange is you have to find the alpha, right? And in Lagrange, you first have to minimize this first, and then maximize the alpha, okay? So first we have to minimize this equation in respect to W and B, in which we have do it accordingly. If you want to see the full derivation is again in that file, right? So once we get that W is nothing but the sum of alpha I, yi, and xi, So you can see that finding alpha is extremely simple, is extremely important because we already have yi and xi. So once we have alpha I, we can already define that line, right? One good question is if we have w, can we find b? And the answer is yes, because we already know that equation, right? That is wtx plus b equal to 0, right? Which is belonging to this line, right? So if we just fill that line, we should be able to get b, right? And we also find that once if we take the partial derivatives in respect to b, we get that the sum of alpha I yi should be equal to 0, right? So what do we do next according to Lagrange? Well, we just plug these two numbers inside this equation. We'll get this fancy equation that looks now we doesn't have any more w, right, and b, because we already plugged everything back. Now we only have yi, alpha I, and xi, and alpha I, right? So according to Lagrange, once we minimize this objective, we can now maximize, that is finding the alpha that maximize this equation, right? And it's very important that we follow the condition of Lagrange, that is alpha I must be greater than equal to 0, right? Of course, a lot of you may feel like, oh, why that is that, right? Well, you have to study the Lagrange equation, and I have already provided you a little bit of details in here, in which is quite lengthy. That's why I do not plan to talk about them in the very detail, but you can always welcome to take a look. So now, how do we maximize this equation? Well, the good news is that we don't have to. We just simply send this equation to some quadratic programming solver, and then it should be able to give you the alpha, right? So now, what is the meaning of this alpha in this Lagrange? Well, the idea is that any I in which the alpha is 0, they are basically non-support vector, right? But if any of the I in which the alpha is greater than the 0, then they are support vector, right? So that is the behind meaning of this alpha. Great. So that is that, right? That is support vector, right? So if you are able to understand the Lagrange method, you should be able to understand support vector machine, right? But of course, Lagrange method is not so comfortable for those who did not understand it very well. So please don't worry too much. Take your time. But again, also don't worry too much, because in the industry, when you actually apply SVM, you simply use scikit-learn. But the key thing you need to know is when to apply it, right? Now, we also can see that we can also, what we have learned is called hard margin SVM. We can also learn something called soft margin SVM, in which we allow some samples to sit inside the margin. That is the widest road. That is right here. So right here, we are using hard margin SVM, right? But sometimes it may be beneficial to let some samples sip into this margin, right? Because otherwise, because things may not be so clearly separable like this. So for the soft margin is actually very simple. The minimization problem may change given some possible errors that you may allow, and the constraint may also change, but the maximization objective of the Lagrange does not change after you do all the hard work, which is good news. Another thing is the kernels, in which because you can see that the maximization objective, it depends on the multiplication of two vector x, then we can actually use a kernel to transform this into another dimension, then we can always find the alpha that help us separate between two classes, right? For those who don't understand kernel, actually, I have a very simple demonstration here, right? That is, if we take if we take two, let's say I have x1 and x2, I can do this kind of things. That is let's say a polynomial of degree 2, right? So the polynomial of degree 2 is something like this, right? Which looks so there's a lot of multiplication you can see, right? So 1 plus 2a plus 2b plus 2abc, right? Something like that. So yeah, we want to move to the another dimension, right? But which you can see that this operation is extremely costly, right? Because it takes a lot of multiplications, right? But the good news is that there's actually an equivalent kernel or the equivalent operations that brings you to this dimension. For example, 1 plus x transpose x prime can also equally bring you to that degree without you computing all these numbers. It will give you exactly the same numbers as this, right? So what is the cool idea? That is, the cool idea is that you can always visit any dimensions in the world without actually computing all those numbers. And there's always an equivalent. There's not always, but there are some operations that can bring you to that dimension without you actually computing all those numbers, right? So in a nutshell, you can translate all these numbers into some dimension such that you can always find the plane that cut across two classes, right? So this is called the kernel trick. All right. And anyway, finally, to make a prediction, what you can do is simply take whatever the x samples and dot product with your WT plus B, you should be able to take the sign. And at the when you apply kernel, you simply take the kernel of the xi dot product with the x test sample. You should be able to take into any space, right? So it depends whether you want to use the kernel or not, right? Great. Okay, so most of the time, once I explain this, students will probably understand around 40 to 50% because there's a lot of equations. So I welcome you to take pause my video a little bit and try to understand most of the equations here, especially the 5 here I provided. All right, so let's take a look through the coding, right? And here I have I have prepared some coding in which I have 3 samples of negative. So you can see that it's upper left quadrant, and here is the positive, right, which is the upper, let's say lower right quadrant. So let me see. Okay, so I run these equations already. So now I need to actually try to see how do I do this SVM with hot function, right? We're going to use this something called CVXOPT library in Python. And but this library is a little bit hectic. It's a quadratic programming library, but it required us to put everything into this format, right? It shares a little bit resemblance to what we have defined above, but we have to change a little bit. So based on this equation, recall that we need to maximize this equation, right? So how do we translate this into this, right? Because we know that we have to maximize this alpha, right? We need to find alpha that maximizes this equation, subject to that alpha should be greater than equal to 0. So I do all this work for you already, so we can let H become this yi, yj, xi, xj, right? And then this equation will become this accordingly. So basically, I just put this as x, and then I just multiply -1 here. So minimize become a maximize problem. Then I can now get a very nice equation in this format, right? But wait, I have to also turn this into maximize, right? So I just multiply -1. Now I get a very nice minimization problem, right? And I just turn this into vector form. So I get this, right? So great. So once you get this and mapping that, you will get all these numbers. That is a P is basically H, Q is basically -1 right here. G is basically -1 diagonal, which is right here. H is nothing but 0. Matrix A is nothing but Y here. And B is nothing but 0, a vector of 0, not a scalar actually. So with that said, I think we can do it right away, right? Give me one moment. All right. So now we can do, so let's take a look at our X, right? So X is not defined, great. So I think I had to clear all the outputs. Restart, run all. Okay, so we got this X, and we also got Y, right? So we have 6 numbers, right? Each of them belonging to and so what we want to find, what we need to find, right? Well, we need to find W, obviously. We need to find B, right? And definitely we need to find the support vector. Which one is actually the support vector, right? So that is what we need to find, right? So first of all, I'm gonna do M equal to N equal to that. So I can do that, and I know that 6,2. The next thing I want is y equal to y dot reshape -1 times comma 1 times 1 dot. I would tell you quickly why do I need to reshape. Oh, reshape is to make sure that this is a 6,1 instead of 6, and multiply 1, making sure that it's a float. That is the only reason why I need to do this, is because the library expect this format. All right. And then now we need to compute h, right? And we call h is nothing but y,x, right? Something in that format. So what we can do is, first of all, I can say x dash equal to y times x, and then x is equal to np dot x dash dot t. Again, you have to multiply in 1 plus, and now you got h. All right. So I think it makes sense, right? Because y,x should be in this shape, right? 6,6. Okay. But of course, if for those who don't believe me that it's actually y,x, you can try to do the math, and it should convince you that is that case. Great. The next, I don't think we need to do anything more. We just need to tell the solver what is P, Q, G, H, sorry, small h. Oh, it just keep giving me that. And then we need to find A, and then B, right? So let me just put a nice equal. And all of them contain something called CVX matrix of something, right? So we have to define this. All right. So what is P? P is H, and Q is nothing but minus NP dot ones, M comma 1, and the minus NP dot I, M. That this is just identity matrix, right? -1. And H is NP dot 0, M. Yep, H is, I think, is NP0. Yep. A is Y. Yep. You may need to read the documentation a little bit, what shapes they want. That would be a little bit that confusing, but yep, once you take a look, it should not be difficult. Great. So once we have everything, now we can, of course, I got some options that I have defined previously. You don't have to do this. I don't think you need to do that. But once you do that, now we can find a solution. So the solution is basically taking the solvers and input all this quadratic programming, and then P, Q, G, H, A, B, and you should get the solution. All right, great. And where does the solution contains is actually inside the X. So let's take a look at the X. All right, and it's a matrix, okay. And why not so in fact, we can do something like this. The solution X contains the alpha. So let's take a look. What is the alpha? Right. So how do you interpret this? Well, based on this, we can already know that support vector is any of this alpha that is, of course, is not exactly 0 because it's a solver. So we have to use our judgment. How do we? So we can see that these two numbers are really the biggest number, right? That is greater than 0. So what we can do is we can say something like 1e minus 4, right? And then we don't want this shape anymore because later on maybe we can use this as a mass, right? So now we can find that according to that, we found that the first one and the last one could be the potential support vector. So let us see whether it makes sense, right? 6 minus 1 and 2, 3, right? So if we go up here, so 6 minus 1 is our support vector, right? 6 minus 1, right? And then 2, 3 is 2, 3 is this one, right? So the system is able to find that, well, the good support vector should be this one and this one. Unfortunately, it doesn't find that 3, 4 is also a very good support vector, but we can also see the alpha, whether the alpha is very small too. So this one, right, is quite good too. So what is this? Yep, that is also 3 and 4, right? So in fact, you can see that this support vector will actually work, right? It actually find which one should form the boundary. Great. So now we need to find the B, and the B is recall that Y is equal to W at X plus B, right? So in that case, we also know that B is nothing but Y of the support vector, right? Minus NP dot X of the support vector dot with the W, all right? But we don't have W yet, right? So we have to construct a W, and W is nothing but the sum of alpha I, Wi, Xi, and Yi, if I'm not wrong. Okay, so we can go up here and recall that is okay. Let's scroll. So we don't need to scroll that much, right? So here we already saw that W is nothing but alpha I, Yi, Xi. In that case, we can find W already because we have everything already, right? So we have to define this equation correctly, right? So I already prepared for you. That is a Y times alphas dot T at X, okay? And dot reshape minus 1, 1. All right. So before I run this equation, let us see what is y. So y is that, all right, 6, 1, and alphas dot shape is 6, 1. So we can multiply them directly, right? And then if we once we dot with x, it's like basically a summation, right? So if we do y times alphas, what we get is this, and when we dot with x, what is x? X dot shape is 6, 2, right? That's why we have to transpose here. Otherwise, because this is 6, 1, right? Then it will conflict. So we have to transpose here and dot with x and reshape it. Then we got w. So let's just see whether we got w. So how does w looks like, right? So that is our w, right? That is the features, the slope for each of the feature, right? Because we have 2 features, right? Great. So once we get that, now we should have a w, right? Great. So this should be our what our b. So let's take a look at our b. Great. So this is we got 2b, right? So we have the w, and now we have b, right? Now I think we are already ready to actually define the line, right? So the line is why not we just use this to predict something? For example, let's say I have some sample is np.array. Let's say we have a samples. Okay, let us go up here, and let's say we have a numbers. We have 2 extreme numbers. Let's say, okay, where's our data? So let's say I have 2 numbers here. Sorry. Let's say we have 1, 1, 3, right? It should be negative. And let's say we have 7 minus 3. All right. Great. So 1, 3, right? And sample 2 should be np.array 7 minus 3, right? And based on this, we want this to be which class? I already forgot. Let me go up again. Okay, let me go up again. This should be negative and this should be positive, right? Right. So we expect that this one to be positive. It should predict positive, and this one it should predict negative, right? Great. So how do we actually do the prediction given that we already have all the W and B? Well, the answer is extremely simple. That is, we just the y hat of the first one is nothing but np dot sign, all right? And you take the W dot with the sample, right? Plus B, right? And now you should be able to get this, right? So okay, give me 1 second. Let's see, because now we don't understand really what does this number mean, right? So first of all, let us do one by one. So W, what is W? W is this, right? So W dot with sample, we got a lot of numbers here. So we have, I think we need to transpose first. Okay, so W dot T. Okay, give me 1 second. W dot shape is 2, 1, and sample dot shape is 1, 2. So if I okay, so I should do sample dot with W, right? I should get one number. All right. And then finally I plus B. Okay, great. So now finally, I think now we can predict, right? NP dot sign. All right. And you can now get the y hat. right? So based on the first support vector, it should be -1. And also the second support vector, it should also be the -1, all right? So we can see that it somehow predict that this sample should be negative. Oh, very strange, all right? Oh, wait a minute. I think we are wrong right here, because here should be negative and here should be positive, right? So yeah, I think we are our equation is correct, right? But this is wrong, right? The next thing we can do is, of course, sample 2. So we can do for the same as sample 2, right? And similarly, we can now print the y hat. And you can see that it can correctly predict that it should be positive, right? For according to each of the support vector, right? Great. So hopefully, based on this, you understand the intuition to how this finding the alphas is the way to find the W, which the W allows you to find the B. And then finally, you are able to use this to predict your samples, right? But when you actually do work in industry, what you do is simply apply them right on using scikit-learn, and that should be fine. Now, there's also soft margin, right? So before that, why not we close everything? And so things are shorter here. So now we have, so let's take a look a little bit. Already prepared all the code here. And I have put a stop here so that it doesn't run until here. So similarly, I think I should put a stop here so that when I click run all, it doesn't run everything, right? So let me just clear the output, restart, and run all, so then I can actually run the soft margin. Okay, great. I assume things are already run. So I prepared some data, and I prepared some numbers that is very nasty and is on this side, right? So how do we actually implement the soft margin, right? Actually, this should be soft margin, not soft max. Why not? I just change this right quickly and search the word soft max. Right, it should be soft. All right, great. So in fact, it's quite easy. We just need to have a condition that alpha I is less than or equal to z, right? And based on that, we just have almost all the same except h, right? In which h now has this c thing, right? So now the h looks like this. So based on that, if you understand everything correctly, you simply put everything accordingly. And once again, you can find the alphas and W and B as well, right? And then you can predict accordingly, right? So there's already only a very small revision, right? That is, you now have a C, right? So that is a soft margin. Okay, and then we also have the kernels. And why not we run all this? And for this code, it's a little bit long, but anyway, I have prepared some kernels. For example, linear polynomial into that degree is simply 1 plus np dot x with that same vector to the polynomial. So you can see that if we want to go to the dimension of 5, we can just do one operations. We don't have to do so many computations, right? This one operations already represent you going to the polynomial degree of 5, right? Which is amazing, right? And then I have also a Gaussian, which basically go to the infinite dimension, right? And we also have a plot. So in my SVM class, I have fit, right? In which I turn every x into my kernel according to my kernel, right? So this is the x and another x, right? So that is the kernel, right? And then what I do is simply putting everything into the solvers and get the alpha, right? And you can see that when I actually want to predict, the most important thing is I need to get the support vector. And this get parameters is nothing but setting a threshold and make sure that I got this support vectors, right? That is according to my threshold. And then, of course, I also compute the W, right? And the B, right? Great. And then after that, I got this support vector. The prediction of is nothing but the W, right? This is the W, right? But because we want to also use the kernel, we deconstruct the y hat a little bit, right? That is, the W is alpha I, yi of the support vector only, multiply with the kernel of xi and xv, right? And finally, I need to plus the b itself, right? Which the b comes from right here, right? And because I have a two vector, I just do a mean, np.mean, so that I can only have a one number, right? So I don't need to worry too much. Sorry, give me 1 second. Sorry. Now, once we do that, we just take the np.sign, and that should be fine, right? And you can see that even in a very weird dimension, right, it can still find that plane that cut across. You may say that, hey, professor, it doesn't really look like a line. Well, this is a line. This is a line in some dimension, right? But when it fold into a 2D plane, it looks like a circle or something. So this is the amazingness of this corner trick. All right. So thank you very much, and hope you understand SVM. If you don't worry too much. It's a quite a complicated algorithm with so many equations, but take your time and study it. All right. Thank you very much, and see you in next class. Bye-bye.